Hi, Ethan. Hi, Hannah. Okay. This I want. This is what I want. Okay, good. Hi, Rhea. Sammy. Hi. Hi, Justine. Luai. Hi, Yanis. Hi, Sam. Okay. Well, we'll have people just coming in just a minute. I'm sure it is 32, and that's okay. I sent you guys a couple emails and also posted it on Classroom. Hi, Steve. Two things specifically about the PhET simulations. Wait, actually, I sent you 3 emails, I think. Anyway, let's just talk about things in general. So we're doing a live stream right now. I'm planning on going. I'm planning on going through the second problem of the 2012 free response on the practice exam. And we'll do that in just a minute. And as before we do that, just a few things I wanted to mention. First of all, in terms of how often we do these live streams, we've been meeting pretty much every time we have class, and I think that's working pretty well. So my intention is to continue doing that, specifically, except for the Doppelstunden. I think that will be a little bit much. So my intention is to meet Monday, Tuesday, Thursday, Friday, in each case for 45 minutes for one period. And I hope that's a good balance for you guys, and it's not way too much or way too little. I'm not sure exactly what you're thinking about that. So that's my plan, and I did send you guys an email about that as well. So sounds good. Okay, so can you just give me feedback quickly in the live chat here, whether that sounds good or okay or bad, or you can express your opinion. Obviously, if you think you really don't want to meet that often, you can say that too, or you can say too little, or you can say too much, or we can just let Hannah's comments stand in space as the only thing you guys say. That's cool too. Sure, Rhea. Good. Okay. Good. Okay. Sure. Okay. Okay. Good. All right. Oh, hey, there's Octave. Okay. Good. So that was one thing I wanted to talk about. The other thing I wanted to talk about, we haven't really had as much hands-on work in the class as one might have hoped, and I'm sorry about that due to time constraints and equipment constraints. We've been kind of restricted, and now we're even more restricted because we're not even in the same classroom. But I have sent you guys a link for or links for simulations online, which I think are very good. And I want you guys to make sure that you, first of all, get that figured out, that it's working for you. And if you just want to play around with it, that's cool too. There are pretty fun simulations, and I selected 7 that are appropriate for this course for E&M in terms of also reviewing what you're doing, kind of getting a feeling for putting circuits together. Hey, what happens if I hook up a capacitor, and all this stuff? And you can, not do it physically, but you can do it in the simulation and figure out where the voltmeter goes, where the ammeter goes, and if you do different circuits, what happens. I think it's pretty cool. There's also simulations on electric fields, which I think are also helpful. Good. So those are those 2 things. I've also contacted you guys about the College Board coming online now with review sessions starting tomorrow. And I'll keep you guys both on all 4 AP courses. I know we are AP Physics C Mechanics and E&M, and if there are relevant reviews there, I will let you know. Thus far, the only relevant review that was posted is one for tomorrow for rotational kinematics, which is sometimes a little tricky. It's for AP Physics 1. Their approach is less mathy, more explanatory, but I think it could still be a helpful session for you guys to attend if you want to. Magnetism will not be on the clausur. We are, and that's one of the funny things. So they posted the review sessions for AP Physics C Mechanics and AP Physics C E&M, and both topics they posted as a review are not relevant to the AP exam. And I will also not make the magnetism, so units 4 and 5, relevant to our clausur, which we're still scheduled to do April 20th. And hi, Claire. And we'll figure out how to do that. But our clausur, April 20th, will be AP Physics C E&M, units 1 through 3. And my intention is to make it free response only in terms of helping you prepare for the AP exams, because the AP exams are going to be free response only. And we'll figure out how to do that. I haven't written the clausur yet. But I'll figure that out. But that's the plan. And hey, maybe we'll even make it 45 minutes. Whoa, just to prepare. I'm not sure yet. Okay. That's correct. We should call the course only AP Physics CE. Right. Correct. AP Physics CE. Whoa. Okay. Good point, Sam. Okay, so if there are no questions, I'll get started on the problem 2, and we can look at that together. I did post it on Google Classroom. If you haven't seen it, I'll hold it up for you over here, so you can kind of take a look at it. Whoop. That's the problem. There we go. So they've got a setup here of some kind of strip of conductive paper, and they've got a measuring device there. Okay, so let's take a look at the problem. A physics student wishes to measure the resistivity of slightly conductive paper that has a thickness of 1 times 10 to the minus 4 meters. The student cuts a sheet of the conductive paper into strips of width 0.02 meters and varying lengths, making 5 resistors labeled R1 to R5. Using an ohmmeter, the student measures the resistance of each strip as shown above. The data are recorded below. Okay, so just kind of making a little drawing of what the heck's even going on. They have a strip of paper. Good. And it has a length. Well, thank you. It's labeled length. And then here, the first one, they've got a width of, oh yeah, I see, it's 0.02 meters in this direction, and that's paper. And then they have this thing connected over here to an ohmmeter. There we go. And they call this an ohmmeter. Okay. So that's kind of interesting. What the heck is an ohmmeter? We haven't really talked about that. Good. So we haven't really talked about an ohmmeter because, like, what the heck does that measure? What is resistance? Well, just a reminder what resistance is. Resistance is defined through Ohm's law. Okay, so that's delta V over I. So it talks about how much, kind of, exactly, but it's like we're measuring voltage per current. So in order for this to work, I mean, if we have this setup going here, in order for this to actually work, we somehow have to have a measurement for voltage, potential difference, but we also have to have a current. Okay, so a good way of thinking about this is that when we hook this thing up like here, there's actually in here an actual ammeter. Well, it is an ammeter, but we're also putting in a little voltage source. Okay, so if an ohmmeter is really an ammeter and a voltage source together, voltage source plus an ammeter. Okay, because what we're doing here is we're applying a certain voltage, a potential difference to this strip, and then we're measuring how much current flows. Because if we figure out then how much current flows, and we know the voltage difference, potential difference, we can use that to figure out the resistance. So it's really, they say it's an ohm meter, but obviously to make this work, we've got to push a current through there. Otherwise, how is this even going to work? Okay, but for now, it's okay to think about this as a black box because they don't really tell you what's going on. And you don't have to know this, but just to make sense of it as understanding how would we even measure this as physicists or engineers. Okay, so that's what's going on, and they're measuring the current, and then the device converts it to a resistance. And they give us data, and they say as the length varies, we measure that there's more resistance. Well, that's no surprise, I would think. So they make a little chart here, and I'll just copy it over here. I'm not going to take up too much space, I hope. There we go. And we have resistor length resistance in ohm. This is in meters. Okay, so there we go. And we have R1, R2, R3, R4, R5. And then we have the lengths 0.02, 0.04, 0.06. Oh, they're very nice. They're being very regular. That's good. 0.10. And then underneath we have the resistance. And I'm going to make my life a little easier by just make this in kilo ohms. Even though that's not what the table says. That means we have 80 kilo ohms here. We have 180 kilo ohms there. 260 kilo ohms there. 370 kilo ohms there, and 440 kilo ohms there. Okay, cool. Now, they're asking us, this is a classic question on the AP. They ask us to somehow make a plot, and they actually tell us what to plot. Okay, they ask us to find on the plot a way to finding the resistivity of the paper. So to coming back to the resistivity, just a reminder is that this is what we call a non-causal relationship. We talked about what kind of relationships there are. Resistance is not caused by current, except if you heat up the light bulb, then it is kind of, well, you get the point. But anyway, it's also definitely not caused by potential difference, okay? This relationship is an algebraic relationship that comes from Ohm's law in its causal relationship, which is delta V over R. Okay, current is caused by potential difference and it's impeded by resistance. That leads to this equation. Well, the resistance of this object right here is caused by three factors, three and another one. Temperature we're going to leave off. But the three factors that cause the resistance of this object are resistivity, the length, and the cross-sectional area. Those are the three factors that together are causing the resistance. Resistivity is a property of the material. Resistivity is higher for some things like styrofoam and lower for other things like aluminum or gold. The length is how long this thing is, and A is the cross-sectional area. Okay, so those are the three things. It's hard to think of this as a cross-sectional area because we're thinking this is a thin strip of paper, but that thin strip of paper does have a thickness, right? So here's our paper, and there is actual cross-sectional area to this. It's small, but there is cross-sectional area. Good. So let's see what we have here. We have different variables. We'd like to know resistivity. We'd like to have the resistivity as our end result that we can get. And to go there, we're going to have to make a plot where maybe R would be Y. That makes sense. Why not? That's hilarious. These jokes, they're amazing. Okay, so we have here Y. And then if we plot L as our X variable, then the slope will be the thing right there. Okay, so that's our plan in terms of making this work. They provided a nice grid for us. So if you want to follow along, that would be good. If you have it printed out, or you can just draw it on paper, that's cool too. Let's just kind of quickly do this. We're not going to be super anal about this. Actually, not to give away how we do this, we're pretty generous on how we grade this. So if you screwed up. Oh, the problem says plot a straight line that allows you to find the resistivity. So it says specifically, use the grid below to plot a linear graph of the data points from which the resistivity of the paper can be determined. Include labels and scales for both axes. Draw the straight line that best represents the data. Okay, so let's take a look. On our X variable, it's L, so it's going from 0 to 10. They were nice enough to give you 5 boxes. 1, 2, 3, 4, 5. And the fifth one is actually edge of the grid. Do use that. Wait a minute, that's not true. They actually give you a 6 box. So there we go. There's a 6 box. Okay, so this is 0.02, 0.04, 0.06, 0.08, 0.1, 0.12. Make sure that you label your axes. This will be a stupid point to lose. They will take a point off for anything that's missing. So over here, we've got our Y variable, which is resistance. R is going to be in ohms. And we're going to take a look at here. It goes up to 440. 1, 2, 3, 4, 5. We can have 6 of these. Good. 1, 2, 3, 4, 5. Going to go to 5 of these. So we're going to go to 100, 200, 300, 400, and that's 5. I'm going pretty small on this graph just to make it sure we can fit it on here. Okay, so now we can plot our data. Make sure you plot your data correctly. That'll cost you points if you screw that up. So 0.02, we're at 80,000. There we go. 0.04, we're at 180,000. Okay, there we go. 0.06, we're at 260,000. 200. There we go. And 0.08, we're at 370,000. Maybe that. All right. Wait, nope, that's not it. There. There we go. And then we're at, whoa, that's straight up. Nope, a little too left. Let's see. Whoop. There we go. And then at 0.1, we're at 440,000. 440 would be like somewhere around there. Okay, does that look pretty good? Looks pretty good to me. Okay, now we've got our graph. Now here's the deal. Do use a ruler. You're allowed a straight edge in the test and actually use it. For the test, we're pretty flexible in grading this. In the past, actually, when we have been in several rooms, isn't R in kiloohms? Yes, thank you. It is in kiloohms. Good point. I would have lost the point right there. Kiloohms. Thank you. Okay. Good. So let's put a straight line in with a ruler of some kind. I'm going to use your twist spool. There we go. And take a look at this thing right there. Okay. There we go. Good. Now, that looks pretty good. Please make sure a couple things when you do this graph. A, that you did use a ruler. B, if possible, and it can be brought through 0, 0, do bring it through 0, 0. However, don't force it, because there are situations where they will ask you to explain why the y-intercept is not 0. Like, what's the physical meaning of the y-intercept not being 0? If that's part like D1 or something like that, and you got it going through 0, 0 because you made it happen, go back and actually change this. Because we see people on the test actually in part D be like, oh, that's right. That's actually the magnetic field of the Earth, or that's actually the weight of the blah, 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 blah. But then they go back and actually change it to actually fix the graph, because obviously there's a mistake. So make sure you go back and check that if you made that mistake. So I do believe it is a proportional graph. I do believe it does go through 0, 0. So that's what I think, which means now we can find the slope. To find the slope, it's important to mark the points on the graph that you're using. Do not use data points. Instead, use points on the graph. So specifically, I'm going to circle the points I'm going to use. We really like you circling them to indicate clearly to us which points you're using. So here you would be using 0 meters, comma, 0 ohms. Okay, and then mark another point over here, and we're going to use a point maybe maybe, I don't know. I'm going to use this point right there. Okay, I'm going to kind of look at it and say, okay, there we go. Okay, that seems pretty reasonable. Okay, so, and again, use the actual grid and use actual like points where as close as possible to an intersection. A 0.1, 0.15. This looks like 0.1, 0.115, maybe 0.115 meters. Okay, good. And then up here, we're looking at 500 kilo ohms. There we go. Okay, so we've got the slope. Now we don't have the slope yet. We have the point here. We have the point here, and we can find the slope. And, oh, maybe just do it over here. That's good because it's over here. So slope is equal to 500,000 ohms divided by 0.115 meters. Make sure you include the unit. That's an easy mistake again for you guys to do. You've got the slope. The slope has a unit. Don't screw up the unit. So there we go. So 500,000 divided by 0.115. You can use a calculator, obviously, for this. Let's go here. So 500,000 divided by 0.115. I get 4.35 million. Okay, so I get 4.35 times 10 to the 6, and make sure we get the unit right, ohms per meter. Okay, that's the number I got. That makes sense. And now let's think about how we're going to use this to find the resistance, the resistivity, which they're asking us in part B. So we did part A nicely. We did a good job. Now in part B, we realized the slope we found over here is just the ratio between the resistivity and the area. Okay, so that's equal to resistivity divided by A. And of course, that means that the resistivity is equal to the area times the slope. Okay, so let's get that value for the area. The area, the cross-sectional area, and this is easy to screw up. They give you here the width of this thing, 0.02 meters, height, I guess, maybe a better word for this, and the depth of this thing, oh, you are, okay, good question, Sam. Always good to come back to this. These points are measurements. The black thing is our scientific model of how we're interpreting the individual measurements. We're using our measurements to come up with a model of how we think nature works. We think this is the nature of nature. That's hilarious. So the nature of nature is that resistance is proportional to length. Now, on the graph, it's not perfect. It's not always exactly the same. And the reason it's not always the same is because each one of these data points actually technically has a little plus minus grid on it. And we're not good at this stuff. So we don't understand how that works. But there's a plus minus for both measurements. Okay, so that means that the data points themselves are actually imprecise. Each one of them is slightly imprecise. Our model, the black line, is more precise than each of the dots. So we apply the model, and then we get the slope of the model, and that value is a better scientific value than if we had used one of the data points and gotten the slope from that, because that is not the slope of the line. Okay, so let's see. The area of this thing, we know that this thing is 1 times 10 to the minus 4 meters thick. So we call it thickness. We'll just write that up here. Thickness equals 1 times 10 to the minus 4 meters. Are we still on the screen up there? Barely. Oh, Sam, exactly backwards. The points are not approximations. The graph is our scientific model and has greater precision than the data points. And they're not actual values because each of your values has imprecision in it. So I'm happy to have a nerd fight with you about this another time. Okay, but we're gonna move on at this point in terms of finding this. But yeah, you're definitely this is better than what you're doing. And all students tend to want to use the data points. That is not correct, and you will lose points on this if you do that. Good. So we've got our thickness as 1 times 10 to the minus 4 meters, and we have our length, and we have our height here. So the cross-sectional area is that length, 0.02 meters, times that length, 10 to the minus 4 meters. Okay, that's a very small number. That's 2 times 10 to the minus 6 square meters. Yeah, good. So 2 times 10 to the minus 6 square meters is the cross-sectional area. Good. So we can plug that in. 2 times 10 to the minus 6 square meters. We can multiply by the slope. 4.35 times 10 to the, whoa, that's cool. That's going to give us a nice number, easier to calculate. Ohms per meter. Let's see, take a look what happens here. Meters squared, meters on the bottom. So one of those cancels. We can symbol, I'm kind of scooching off. I'm going to make sure. So one of these cancels. And then we're left with 8.7 ohm meters as our answer. 8.7 ohm meters is our answer to part B. Oh, and please tell me that's correct. We have the solution. Yep, they got 9. Ooh, they say it's not acceptable, plus minus 0.2. We're a little bit too far off. But again, we threw this on the board, and if we actually use the grid, we can probably get better precision. Okay, so we did A and B okay. There's our answer. They have 9. That's all right. And there we go with parts A and B. Okay. Any questions so far about parts A and B? I'm going to take a picture, and I will post this later for you. All right. Does that work? Excuse me. You're looking at my ceiling for a second. I need some more space here. There you go. All right. Okay. Back to you. All right. There we go. And I'm going to erase this now. Oh, okay. Super. That's a good question. So when we're looking at the area is the cross-sectional area. And this device is weird, okay? Because this device looks something like this. So this is our device. This is, instead of using a wire, we're using like a thin piece of paper that's like made of some kind of carbon material or something that does conduct a little bit. And if you're the electrons, you're not looking at this as your cross-sectional area. You're looking at that. You're like, ah, crap, that's really small to get through. And that's going to be a really narrow hallway, like the 7th grader hallway analogy that we talked about. Hard to get through because it's very, very low cross-sectional area. This is actually the length of the hallway that you have to get through. Okay, I'm going to erase that, and then we're going to move to parts C and D. I think there's parts C and D, and we'll go from there. So let's erase this part here. All right, we still have the I don't know if we need it, but it's there. Okay, good. All right, let's take a look here. That's part A, that's part B. And now we get to part C. Oh, yay. So, completely erase this because this is pointless. So, this is kind of a classic part C a little bit here, where they're thinking, oh, okay, well, that was kind of a fun little thing, and now we're going to do something completely different, kind of. So they take a battery, okay, and the battery is over here, and they have this thing right there. There's your battery, and they connect the battery to 2 of these, okay, one there, and there's a longer one is R5. There we go, R5. And then we have a shorter one next to it, and this is R4. Okay, and now that's just a weird thing to do, but they have 2 resistors basically here. And then after that, they have a capacitor. And I'm done with drawing this like this. I'm just going to draw in the circuit diagram here. This is weird. Okay, so there we go. And boom, there we go. So this is the positive end right here. This is the negative end. So we connect this thing. They have a switch, first of all, here. There we go. Here's the switch. A little bit confusing. Okay, either way. 2 resistors. The 2 resistors are in parallel, okay? So together they will have less resistance than either one of them would have by itself. Important to realize that. We have our values for R4 and R5. R4 is 370 kilo ohms, and R5 is 440 kilo ohms. This is this one here, 440 kilo ohms. That's our situation. There we go. Now, they ask us now to find the time constant. Okay, now this is one of those things. You get relatively little points in physics from memorizing stuff, but occasionally something is really helpful. Okay, so in this case, remembering what time constant means, okay, it refers to the idea that all the stuff we have in terms of voltage, potential difference, current, amount of charge. In those equations, there's a number in them that looks like this. So you have e to the minus t divided by RC. So everything is kind of proportional to that, or it's 1 minus that, or something like that. Okay, so this thing right here comes up all the time in all the equations, and the time constant, well, that's just this thing right there. So if you just remember that time constant is RC, you're going to be in good shape. And they give you actually a point just for writing that down. Okay, so there it is. 1 point secured, nicely done. Now we need to figure out the resistance of these two together. Because they're in parallel, they add inversely. Okay, so for this thing, we can say, the resistor here. Oh, crap-a-roo. All right, I need a black marker. Here it is. This one, it was kind of, we replaced this with a total resistance right there, or an equivalent resistance, okay? For that equivalent resistor, 1 over R tot is equal to 1 divided by 440 plus 1 divided by 370. And as I've indicated to you guys, I don't believe in fractions. I do believe they exist, but if you put this on the same denominator, I mean, are you kidding me? That just seems dumb. Okay, anyway, so I would just punch this in my calculator. So if I punch it in 1 divided by 440 equals, and then you add to that 1 divided by 370, you get out a number. Okay, if you want to first write it down because you're afraid you're going to screw it up, that's cool. R tot is equal to 0.00498, and then the total resistance is the inverse of that, and that gives me 201. 201. Now, don't screw it up. I used kind of shorthand because of the whole winning World War II thing, but here you have to remember that this is kilo ohms, so the result should be in kilo ohms as well. Kilo ohms. There we go. So 201 kilo ohms is the correct answer for R, and they give you for the capacitance a value of 10 microfarads. So there we go. We put that in. We get 201. And let's just write out the numbers. I don't know if that's helpful. Ohms. We multiply that by 10 microfarads. Okay. I'm actually going to switch gears here for obvious reason. Okay. Times 10 times 10 to the minus 6 farads. So I rewrote it to allow us to do this more easily. So 10 to the 6 cancels out 10 to the minus 6. So we get 2.01. And then it's like, what the bleep is an ohm farad? It's an ohm farad. Well, it's a second, actually. So it's 2.01 seconds because the time constant is, of course, a time. All right. Any questions about part C? Okay, no questions about time about that part. We're going to quickly take a picture. We only have 6 minutes, but I think we can do this. And then we can make the graphs, and then we're good to go. Okay, good. And they're specifically asking here, they're asking for the voltage, capacitor voltage, and the voltage across each of the resistors. Okay, so here we go. Potential difference is really what we use. So I'm going to label this delta V, and we specifically have 2 of them. And let's use maybe delta. Oh, let's use two colors. So delta VC, and then we're going to use delta VR as the black one. Okay. So as time goes on, this is time, and there we go. So what is going on when we close the switch? Where's the voltage drop? Is the voltage drop across the capacitor, or is the voltage drop across the resistor, or are they both in the beginning non-zero? Okay, you're unsure. I'm going to give you a reminder. Charge on a capacitor is caused by a voltage difference. And then you end up having a certain amount of charge on there based on the capacitance. That is correct, Sammy. Okay, so initially, if we want to solve this for delta V is equal to how much charge you have on the capacitor divided by the capacitance. Initially, we have no charge. Therefore, there is no voltage. Okay? On the other hand, our resistor has the full delta V because there is a current flowing through that resistance. Okay? And the current will die off as charge builds up. So that means that this one increases, this one decreases, but the sum of the two will always be the same, of course, because the sum of the two has to be the total potential difference. Okay? The color workout, black workout, okay here? There we go. And if we did the sum of those two together, say in blue, this would be delta VC plus delta VR. It would be that value there, which is equal to the battery's value for the potential difference. Okay, good. And that's part D, and that brings us to the end of the problem. And I think that's a good review. We have talked about capacitors, time constant, parallel resistance, resistivity, some good stuff in here, I think. Okay, so do you guys have any more questions? We only have 2 minutes left on the clock for today's class. Okay. I am planning on tomorrow. I did want to mention one more thing. Doing a. Oh no, they acknowledge that R4 and R5 are the same in the problem. So if you look at the solution, there are just two voltages plotted, and they just label it R4 and R5. So we don't need to do that. So on Wednesdays, I will start an office hour as well as a live stream, and I don't know what's going to happen. That's going to be during lunch, so 12:20 to 13:05. And I'll be available on here, and it's open to any of my classes. So, but if you guys want to come over here and ask a question, that's cool. I have a feeling that maybe you guys. Do we need to do all the AP classroom homework? Because I have a for your total grade. I focus on doing this stuff for the units that we still have on the exam. I haven't looked at AP Classroom again in terms of those things, but do the work for those things. Keep doing work to prepare yourself for the AP exam and worry less right now about your course grade. I know that's difficult, but we'll figure it out, Yanis. We'll figure it out. So tomorrow, 12:20 to 1:05. is going to be my office hour. If you want to pop by and take a look and maybe ask some questions, feel free. But I am opening it to all my classes, so I don't know what's going to happen. But thanks for coming. And otherwise, I'm planning on seeing you guys on Thursday during the time I sent you guys, which I think is second period. But I sent you the time in the list, and then we'll meet on Thursday, and then Friday, Monday, Tuesday, Thursday, Friday next week, and then we have spring break. Yay, spring break! We are not going anywhere. Okay, all right. Thanks a lot, and see you guys later.